you like to take questions in the middle or at the end?
Anytime a student wanted to stop me, that's fine. I'm very flexible.
Okay, so then they will post it on the chat box, so I can read it out to you when they post the questions.
Okay, and you can just wave to me and stop me and during my talk, and we can start.
Okay.
Start answering questions.
Okay, fantastic. Okay, that's good. So welcome everyone. It is an honor to introduce Professor Juni. He's a scientist at GILA and NIST and a professor at the University of Colorado. He's a member of the National Academy of Sciences in USA, a fellow of the American Physical Society, and a fellow of the Optical Society of America. He has received numerous awards and honors, too many to read out. This includes the Messias Quantum Prize, the Norman Ramsey Prize of the American Physical Society, and the II Rabi Prize of the American Physical Society. Professor E leads a research group which works at the very forefront of many aspects of ultracold atoms, molecules, and light matter interactions, and has made seminal contributions in essentially all of these fields. He is well known for his works on precision frequency measurement using frequency combs. The technique has transformed the way frequency is measured to sub-hertz accuracy these days. His lab is also the home to the most precise and accurate atomic clock, which is based on ultracold strontium atoms. It is a testament to more than a decade of dedicated work and has a stunning uncertainty at the level of 10 to the power minus 18. His lecture will, however, be on a different topic, on ultracold molecules, which is again a field in which he is a world leader. The first report on a high phase space density gas of polar potassium rubidium molecules came from his lab in the year 2008. Subsequently, his lab surpassed many milestones, including the recent demonstration of a degenerate Fermi gas of polar molecules. We are very fortunate to have him as a speaker in this school today. Welcome, Professor D.
Sourav, thank you very much for your generous introduction. Yes. So let me share my screen. You can see the screen, yes?
Yes, I can see.
Okay, perfect. Let's see if I'm going to turn on my, should be able to find this laser, the tool of my laser pointer. Well, that maybe it's okay. Can you see my mouse moving around on the screen?
Yes, we can see.
Okay, I will just use my mouse. So, well, thank you very much for inviting me to come to this AMO summer school. And hopefully, as Sourav already introduced, I'm going to tell you a little bit about the story of molecules. I know that Christoph also gave a talk about molecules. And you can see in the people coming from different perspective, or at least from my perspective, I would tell you what's so exciting about molecules, okay, in the next 2 lectures. And I structured my lectures in 2 parts. The first part will tell you more general sort of a cold molecule field, and of course, highlighting some work that's happening in our lab. Tomorrow's lecture will be focused on really the quantum gas of molecules, and to tell you the excitement of what making molecules in the quantum regime that will bring to us at different fronts of the scientific studies. So let's get started on that. And as I mentioned earlier, if you have any questions, please do ask during my lecture, and I don't mind being interrupted, and I will be happy to get everybody on the same page so that we can move on without having questions lingering, because otherwise it will affect your sort of enjoyment of the lecture if you have questions. So we all know that probably you already appreciate very much why we are studying ultracold matter. And in Sourav's introduction, he already mentioned some of those deep reasoning for it. When we make atoms and molecules really cold, bring them into the quantum regime, we can achieve the most precise control of quantum systems because all the entropy is gone. And it really sort of implementing textbook level of quantum state engineering and control of atoms and molecules brings to us this fantastic new excitement of quantum information science. You hear all about quantum computers, quantum simulators, and so on that will be covered in the summer school here. And the clocks, quantum sensors, all of this builds on the capabilities that we developed over the recent 2 decades or 3 decades of precise control of ultra-cold atoms and molecules. They, of course, by being able to control individual quantum particle states really well, it allows you to build up system from bottom up, as people say. You know, once you have a microscopic control of individual atoms and molecules, you can bring them together one by one and actually study the quite interesting phenomena of how the complexity emerge from very simple rules governing how two atoms interact or how two molecules interact. You bring a third one, you bring a fourth one, and you start to see this emergence of complexity. And that's really very different angle of studying many-body physics from traditional condensed matter physics, where you have already a piece of material and you have to figure out the universal governing principles underneath these advanced materials. Here you can build a system up from scratch, from bottom up. So that allows you to shed deeper insights, or if nothing else, complement the studies people traditionally do in condensed matter physics. Excuse me. And that will allow you to study sort of universality, scaling of different energy scales, perhaps probing some of the most outstanding questions we still have, such as superconductivity, quantum magnetism in condensed matter physics, where we can use really cold atoms or molecules to mimic electrons. And of course, energy scale is very different. We're talking about something which is at a nanokelvin of energy versus something which is at room temperature or at a Kelvin at most of superconducting materials. And you know, but of course you will say, how can I use such a cold systems to represent something which is at room temperature? Well, that's because everything can be scaled in energy. You use optical lattices to mimic ionic crystals. In that case, the density, the spatial density of optical lattice is of course many, many orders of magnitude below what a traditional condensed matter systems will offer you. So by scaling everything down, the thermal energy, the kinetic energy, the interaction energy, the density of the system, you can achieve, in fact, similar Hamiltonians describing the system dynamics. And because the system of cold atoms, molecules can be built up from ground up, this allows you to actually, in a controlled way, implementing defects, implementing system dynamics, and so on, driving the system with different Hamiltonians, and so on, understanding where the dynamics coming from, understanding whether the dynamics you're studying is universal, is scalable, and so on. So that's really been sort of the motivation of why ultra-cold matter has been at the forefront of AMO physics for the past few decades now. And as you can see, touches on many different fronts. So these are classical pictures by now. It's already more than 25 years ago, people realized the Bose-Einstein condensate, where it's a very much a macroscopic quantum phenomena that you can realize even with your naked eyes. You can actually see quantum mechanical waves of these atoms that, you know, a million or so of them combined into a dilute gas with a density of 10 to the 12, 10 to the 13 per centimeter cube, a temperature of a few hundred nanokelvin. You have this macroscopic quantum mechanical wave function describing the collectiveness of the individual atoms that working together with their de Broglie wavelengths overlapping with each other. And of course, that has brought us the phenomena of superfluidity. And people have studied how the phase transition from superfluidity to modern insulator physics. And this is, as you can tell, this is very much traditional condensed matter physics, but now you can use quantum gas of atoms to study that. There's also Fermi superfluidity, the gap of the Fermi pairing, and so on. So all of that has shed new light into the strongly correlated phenomena. Yeah, that's traditionally studied in condensed matter. And the reason why we have made so much progress in this field is really comes down to two ingredients. One is being able to, of course, after you are able to control individual quantum particles, you want to be able to control how they interact. So control atomic interactions is a key. And these two aspects of being able to control atomic motion, being able to control atomic interaction in the quantum regime brings up all this wealth of new phenomena that we can study. And so now let me bring it up to the cold molecules. Why cold molecules are interesting. And this is something perhaps you can consider a fairly simple picture, simple-minded. When we describe how two atoms interact, you may have already studied this, the so-called contact interaction. When two atoms come together, they deform each other's electronic potentials, and typically this so-called induced dipole-dipole interactions gives rise to the van der Waals potential. The interaction is described as a short range. Some people call it contact interactions. It's isotropic. Now, when you have molecules, especially polar molecules that can be polarized under electric field, well, we all know we have a dipole moment. Once you have electric field define the quantization axis in the laboratory frame, the molecules which initially does not possess any dipole moment, only in their body fixed frame, you have a dipole moment, but not in the lab frame, because otherwise you would be violating time reversal symmetry. But once you apply electric field, you can induce the alignment of molecules with respect to the electric field. And that's where you can have a measurable dipole moment in the lab frame, or you can consider these molecules as oriented under the electric field. And with dipoles, we know that even going early on at the college level of physics, we have studied the dipole-dipole interactions, where it's anisotropic, depending on the interaction angle, the angle between the two molecules, how they're oriented with respect to the lab frame. And it's tunable. The dipole moment can be made smaller and bigger by controlling the electric field. Compared to the isotropic contact interaction of atomic species, the dipole interaction tends to be much stronger and a longer range. It's 1/r³ instead of 1/6 in the van der Waals interaction. So that brings up really interesting aspect of using dipolar quantum systems to study new aspects of a strongly correlated quantum material, to study system dynamics where you can control the interactions with tunable Hamiltonians. And so here shows some pictures of these molecules confined in optical lattices. And it's particularly on the bottom right corner, I'm showing a system that's just being now realized in our laboratory, where you can have individual two-dimensional traps, looks like pancakes, one layer at a time. Each layer you have a Fermi-degenerate degenerate sea of molecules. They're random in the sense of moving around as in a Fermi sea. Of course, at ultra low temperatures, their quantum mechanical wave functions start to overlap. But between the individual layers, you would consider them as independent. But if the kinetic energy of the molecules is lowered to sufficiently to a point where it's becomes comparable to the dipole-dipole interaction between these molecules, between different layers, then you can start to see the emergence of correlations between individual layers. So this will be an outstanding new quantum systems to study this emergence of orders between previously disordered independent pancakes of molecules. And of course, you may have also heard, and in fact, this topic is also covered in the summer school, where atoms, of course, possess magnetic dipoles. And you may have heard earlier today even. And so people have been studying atomic magnetic dipole interactions for a while. And you may ask, well, why do we bother to study molecular dipoles if an atomic magnetic dipole can already bring us a dipolar quantum system? Well, if you remember in electromagnetism, when you study electromagnetism, when you compare dipolar interactions, typically a dipole is a canonical unit to describe electrical dipole, and a Bohr magneton is a canonical unit to describe magnetic dipole. The scaling between the dipolar interactions among two electrical dipoles versus two magnetic dipoles goes with roughly speaking, debye squared of Bohr magneton squared times the speed of light c squared. And this is something basically from the basic E and M. You can derive that. So if I have a 1 debye electrical dipole moment, and I bring this together to have a dipole-dipole interactions, that strength is 10 to the 4 times bigger than the magnetic dipole moment. So if you want a strongly interacting quantum system, electrical dipole brings this opportunity for much stronger interactions than magnetic dipole that's possible. But another really important feature is, unlike a magnetic dipole, as you know, magnetic dipole exists with a persistent current in a single quantum state, but electrical dipole does not. Electrical dipole in a single quantum state, you won't have a parity violating electrical dipole moment. You have to use electrical field to induce parity mixing between the two opposite parity states, and that will induce an electrical dipole moment. And this electrical dipole moment, therefore, is tunable by the external electrical field. The external magnetic field can only tune the orientation of the magnetic dipole, but electrical field can allow you to both orient the molecule, but also tune the dipole strength. So that means you can implement a Hamiltonian that's both tunable and anisotropic at the same time. And that's another feature that magnetic dipole does not have. So that brings a really interesting aspect of molecules for strongly correlated quantum systems. But of course, molecules goes far beyond that. And it turns out molecules possess some really interesting properties that atomic physics does not really offer. Molecules are much more complex, but at the same time, once you are able to control that complexity, it brings some unique features it touches on fundamental physics, such as fundamental symmetry problems, such as the problem of the existence of the asymmetry between matter and antimatter in the universe, for example. The fact that standard model of the current physics is not complete, that we know we have dark matter out there. There are things that are waiting for us to discover. And molecules actually provide a very interesting platform to study fundamental physics. Here I'm listing an example of people doing so-called search for the electron electrical dipole moment, meaning that electrons may possess permanent electrical dipole moment. And as I just explained earlier, if you don't have electrical field in the laboratory frame, there should not be an electrical dipole moment, because it would violate time reversal symmetry or violate the parity conservation. And it turns out that's exactly the reason why people want to study and search for the electron electrical dipole moment, because its existence would give rise to the confirmation. Of course, we already know CP is violated, charge parity is violated, or time reversal is violated, its symmetry. But the violation at the moment is too small to explain the matter-antimatter asymmetry, or really brings up together of allow you to peek into the corner of standard model where people are proposing super heavy, supersymmetrical partners to existing particles that we know. And electrical dipole moment will allow us to place a fairly stringent bound on the so-called extension of standard model theories. So one study people are having been looking at electrical dipole moment is to do this in a cold molecule experiment, where the molecule, because it possesses electrical dipole moment, meaning the molecule can be oriented with respect to the laboratory electrical field. So by applying a relatively small electrical field in the laboratory, you can orient the molecules either parallel to the electrical field or anti-parallel to the electrical field. And depending on the angular momentum coupling of electrons within the molecule frame, you can, in some sense, flip the electron spin up and down. And if the electron actually possesses a permanent electrical dipole moment, this will give rise to a very minute, but yet detectable energy level shift. So if you do very precise spectroscopy work under the different electrical field as you orient the molecules up and down in the lab frame, you'll be able to place a stringent upper bound of the existence of the possible electrical dipole moment. Currently, the best measurement is done by this collaboration called ACME, Harvard, Northwestern, and Chicago now as collaboration, where the existence of dipole moment is being confined to 1 × 10⁻29 electron centimeter. And similarly, at JELA, we are also pursuing this electrical dipole moment measurement for electrons. Here we use trapped hafnium fluoride ions. And the reason I'm bringing this up is only want to show you that by cooling molecules down, confining them in a trap and so on, you can extend very long coherence time. And if you want to do high precision spectroscopy or building atomic clocks or search for electrical dipole moment, going for long quantum coherence is a key, because that allows you to be able to tune up huge sensitivities to see a minute energy shift when you are changing external parameters, such as electric field. So you can see the JELA measurement from a few years ago, 2017, is placing the dipole moment at a bound of 1 × 10⁻28, an order of magnitude less stringent than the most recent ACME result. But the JELA result is in fact about to be revised very soon, as the measurements are now taking place with a much improved sensitivity by a factor of 10 or even 100 or in terms of statistical sensitivity. So this is going to be really exciting to see continue to advance the frontiers of precision measurement with relevance to high energy physics, search for unknown particles using the techniques coming from ultracold molecules. So that's another aspect of why molecules is interesting, not just coming from the aspect of studying many-body physics, trying to correlate the material, but from precision measurement point of view. And yet another front, the molecules are very interesting, and this is actually what I'm going to talk about today, is also touching on the so-called ultracold chemistry, where the chemical reaction process is all about bringing molecules together, have them rearrange themselves, have a chemical reaction where you have a different molecular species coming out after they reacted. But traditional chemical reaction, of course, is studied as if you're putting different solutions together, and you bring solution from one test tube to the another. The color of the solution changes, the smoke coming out, and so on. Feels like it's something typically uncontrolled. It's naturally occurring process. But if you study the most basic level of chemical reactions, when you bring 2 molecules together, watch them transform to another 2 molecules, 3 molecules, whatever you want to call them, as an end product, then it would be fantastic to be able to follow the entire transformational process of the reaction, starting from how you control the reactants, how the 2 molecules come in together, what particular quantum state you can prepare them, controlling their relative collisional motion, and then bring them together and control the reaction barrier, for the example, using electromagnetic fields, and maybe even bring some resonances, bring the 2 molecules when they come together, when they have some interaction barriers, and they can have a tunneling process and so on. And finally, you want to be able to have a very sensitive detection to analyze all the final states that will allow you to see how different quantum state of initial reactants dictate particular pathways for chemical reaction to go. So this brings together a fundamental insight of this transformation of a 4-body physics, 5-body physics, when you have 2 molecules coming together and the different constituents gets rearranged, and in a process which can be fully controlled, or at least fully understood. So this is a new aspect of chemistry, physical chemistry, that's I think are going to be revolutionized by being able to control the molecules at their quantum state, both internal and external degrees of freedom. So that's the other aspect of cold molecules can have a major impact to science. But of course, molecules are very complex. The reason why the cold molecules have lagged behind atoms is because of, well, excuse me, I'm just going to go to turn on my office light, just to turn on by itself. the light switch is too smart. It turns off it by itself if I don't move enough in my office. So sorry about that. The molecules are complex, right? If you look at atomic physics, where the whole point of bringing atoms into quantum degeneracy is to cool them down such that every atom behaves the same way. Their quantum mechanical de Broglie wave start to overlap on top of each other. For molecules, well, there are lots of internal degrees of freedom. And this is really interesting. You have one atom, meaning you have a nucleus, and then you have electron moving around it. So from that perspective, there is no nuclear degrees of freedom to speak about. It's just electronic states you have to control. When you have molecules, even if you have just so-called diatomic molecule, when you have two atoms forming a chemical bond, forming a molecule, these two atoms, two nuclei, can vibrate. They can rotate around each other. They can have hyperfine interaction due to nuclear spins. And suddenly now you have a large scale of energy landscapes beyond just electronic degrees of freedom. Of course, you have electronic degrees of freedom that gives rise to the so-called molecular binding energy, a few thousand kelvins. And then you have the degrees of freedom of the two nuclei can vibrate. And typically that's a few hundred Kelvin worth of energy. And then the molecules, of course, can rotate. And you can have, sub-Kelvin kind of energy scale associated with rotational degrees of freedom. And you have a micro-Kelvin energy scale associated with how then the magnetic moment of the nuclei interact with each other. All the way down to few hundred of nanokelvin of translational energy, which is needed, where you can bring these quantum mechanical waves or de Broglie waves of individual molecules to be sufficiently long-ranged that they can overlap with each other so that you can bring the molecules in so-called quantum degeneracy. And as you can see, you have to cover a large range of energy landscape. This is actually not that hard. We have lasers. Lasers have photons. Photons can give rise a very large EV worth of energy. So maybe that's okay. But it's the problem is when the molecules you bring a molecule at room temperature. We all know that you have studied the partition function in statistical physics. And all the degrees of freedom, vibrational, rotational, hyperfine interaction, all the degrees of freedom are occupied. And it's this tremendous amount of entropy hidden inside the internal degrees of freedom of the molecules make this task particularly challenging of bring every molecule to a single quantum state and have them to have either Bose-Einstein condense or make a degenerate Fermi quantum systems. So that's the reason why. And I'm just going to belabor that point a little bit. I use the KRB. This is the topic I'm going to talk about tomorrow. But since it's very easy to describe, you have two atoms, and you can start with two atoms which are free from each other. And then I can teach them how to form a molecule in the ground state. And in between, you can say, well, there are actually a lot of energies in energy states lying in between. The binding energy, the electronic energy is on the order of 6,000 Kelvin, as I mentioned earlier. But if you zoom in, of course, within that electronic potential, there are many, many vibrational quantum states, hundreds of them. And so you would have to making sure that when you make a molecule, if you want to make every molecule to be identical to their neighbors, you want to make the molecules to all occupy a single vibrational quantum state. Okay, so let's do that. That's already itself a bit challenging. You have hundreds of quantum states. You have to go to the very bottom of it. Now, suppose you were able to do that, and you pull out a magnifying glass. You look at the energy scales. You can see, well, that single vibrational quantum state itself splits into many, many rotational states. And those rotational levels can also have hundreds or thousands of them, and they can have a different energy scales. So again, you have to bring all the molecules to a single rotational state. And even after you have done that, there's also nuclear spin states. And you can have tens of different nuclear spin states, depending, of course, on the existence of the nuclear spins you have in your molecular system. And those are typically, it's described in energy scale that's lower from the rotational energy scale by a few thousand times or a few tens of thousands of times. And the question really is, you know, you have all these states that's occupied by molecules with all these entropies that are describing at a high temperatures, all these quantum states will be occupied, right? So in order to really cool the molecules down, you have to make sure that all the entropies from these internal degrees of freedom are driven out, are removed. So the molecules occupying a single vibrational state, a single rotational state, a single nuclear spin state out of a single electronic state. So all of that, if you can do all of that and still have translational degrees of freedom being under control, then you finally have a chance to bring molecules into the quantum degeneracy, into the quantum regime. And so that's really the main challenge of bringing ultracold molecules for play in our quantum game. And if you have seen, if you open any molecular spectroscopy book, you see this very typical pictures of these, you know, in the early days, 100 years ago, when people started to record molecular lines, you were using photographic plates like this, and you'll see many spectroscopy lines. And that's because all these lines corresponding to these many degrees of freedom I just described. And you would have to really making sure that all of the lines disappear if by the time you can control all these molecules into a single quantum state. So how do we do cool molecules now with this understanding of being very complex? Well, one technique, of course, is the nature has already brought us molecules. After all, we are all made out of molecules. So you already have chemistry happening in nature. Now the key thing is, can we bring these molecules to a lower temperature by using different techniques? So that's one way of doing it. People call it direct cooling of molecules. Another way is that since we have been very successful in cooling atoms to very low temperatures, what if we do new kinds of chemistry where you bring two different species of atoms from your periodic table, and you were able to bring them together and teach them how to form a molecule. In doing so, without increasing entropy. If you can do that, then you can go from ultra-cold atoms and going through this quantum control steps, making ultra-cold molecules, because you already have made ultra-cold atoms. So that seems like another very natural way of making very cold molecules. The challenge, of course, as I described earlier, is to be able to traverse this many different energy level structure states so that you can reach all the way to the bottom of the ground state in a single quantum state level, so that the molecules that you create out of ultra-cold atoms do not possess additional entropy that you have from your original ultra-cold atomic system. So that's the challenge. And the second topic I'm going to describe tomorrow, but today I'm telling you mostly on the first topic, which is the so-called direct cooling of the molecules. And so if you look at the phase space picture where the vertical axis describes the spatial density, how many molecules you have per centimeter cube. The horizontal axis in log scale describes the temperature of the molecules. And altogether, the spatial density and the temperature, of course, describes the actual phase space density. And so there are various different techniques people have invented: buffer gas cooling, deceleration of molecular beams, photo association, and all these various different techniques are trying to cool molecules down. But unfortunately, the phase space density of these techniques tends to be relatively low, on the order of 10 to the minus 12, perhaps. So 12 orders of magnitude below the unity where you use to describe phase space density equals to 1 is when the de Broglie waves of neighboring quantum particles start to overlap with each other. And that's when you enter the quantum degeneracy regime. So there have been recently, over the last 10 years or so, have been a lot of effort in doing laser cooling evaporations, sympathetic cooling of molecules, to try to further advance the higher phase space density. You want to go to higher phase space density, you want to go to higher spatial density, you want to go to lower temperature, because the de Broglie wavelength is inversely proportional to the temperature you have in your system. So this arrow towards quantum system regime is showing towards going to the upper left corner, where you have a increasingly large spatial densities and increasingly lower temperatures, tens or hundreds of nanokelvins. right now we do have a quantum system, as Sourav mentioned earlier, that we do have a system that get us into the quantum regime now, where the molecules, the Broglie waves overlap on top of each other, and we get into the so-called Fermi degeneracy. And I will describe what Fermi degeneracy means tomorrow. So there are some quantum systems that we can get into this incredibly cold and incredibly dense regime. So this brings me to just give you a quick summary of 2 lectures I'm giving you today and tomorrow. The first one, the lecture 1, all that discussion I have had so far is introduction material, but finally getting into, what we are going to use cold molecules for quantum state resolution spectroscopy. And I'm going to give you an example of, you have heard about molecules that called a buckyball. This looks like a soccer ball. And I will tell you a little bit about what a new quantum state resolution has brought us, what new insight has brought us to this fantastic object of a buckyball that's following C60 molecules. I will tell you a little bit of laser cooling of molecules, and also tell you something about in chemical reactions. How do you really study intermediates? It really try to understand the chemical reaction pathways by developing new tools such as a frequency comb. Again, Sourav's introduction, he mentioned that. In lecture 2 tomorrow, I would focus on actual quantum gas of interacting molecules, where we can now build these molecules with exceedingly low entropy, putting them into optical lattices or putting them in different spatial geometries, and you can turn on electrical field and tune the interactions between those, shield yourself away from chemical reactions, and study resonances even among these 2 molecules, how the molecules interacting. And that's a really exciting new topic. Some of the advances I'm going to cover tomorrow are very new. In fact, started some of the work, of course, accumulated over many, many years, but some of the breakthroughs happened all over the last 12 months or so. So I hope to convey some excitement. At this point, maybe I'll stop here and just ask whether there are questions or not. If there is no question, I will go forward. But if there are questions, I'll be happy to answer some.
There are none on the chat box, at least.
Okay.
Yeah, so maybe you can just go ahead.
Okay, I will just go forward then.
Right, I'll let you know. Thanks.
So the first interesting aspect of the molecules, as I mentioned, it's not just for physics. And of course, chemistry and physics are interconnected. We call it physical sciences. But to just continue to understand large-scale complex molecules, and if the system is too hot, it's very hard to understand this from a microscopic point of view, how the complexity comes about. If you can cool the system down, then you can actually putting back energies into your system 1 quanta at a time, so you can actually understand the rising of complexity from that. So one area that we have had over the last decade or so is to study increasingly more complex molecules. As the number of molecules, number of atoms in a particular molecule increases, of course, the energy landscape becomes more and more congested, and it becomes more and more complex. To a point, we can study actually C60 molecules, and it's a fantastic system. And we actually, in fact, in order to do that, we had to develop some technologies, such as a mid-IR frequency combs to do that work. You can think of in the bottom panel, and it's just a technology that's very useful for cold molecules. That's why I'm not going to tell you about how frequency comb came about or how that works, but except to let you know there is such a fantastic tool around where you can essentially look like a rainbow. This color is invisible in the early days, but we can now make those big rainbows in the mid-IR. Of course, your eye won't be able to see it. But what's fantastic about this kind of a new form of light is it has a structure of comb-like frequency markers in a very regular spaced fashion, marching across, giving rise to tens of thousands of frequency modes but you know exactly where they are, and you can use them as a probing channels to look at the molecular, vibrational, rotational absorption signatures. And so that's a tool we're going to use to study C60 molecules. And in fact, you can think about such tools as tremendously useful if you want to study how molecules come together, have a chemical reaction, generating intermediates, and then proceed to final products. If you have a tools like that, being able to follow various different species being generated during the chemical reaction by just looking at their vibrational rotational signatures using these tools like frequency combs, then you actually gain a fundamental new insight of the actual very complex reaction pathways when molecules are rearranging themselves, reconfiguring themselves. So you must have heard Buckminster Fullerene C60, and that's actually discovered back in the 1980s. So this has been already more than 3 decades ago, right? And it's one of the 3 isotope form of carbon, like after diamond and graphite. People just love that kind of the way nature has structured these atoms, 60 of them, together in such a highly symmetric way of arranging themselves. And it has played a tremendous role in carbon nanoscience, in astrochemistry. People have actually seen this in so-called carbon stars, where there's a strong signatures of C60 out there in the outer galaxy. It's a highly symmetrical. It's in fact a very rare example of icosahedral point group. There's 128 symmetry groups in this one molecule of C60, and looks like a soccer ball. If you truncated icosahedron, is of course a soccer ball that we play. And to our surprise, though, this molecule, after it's been discovered, people have studied the electronic properties of it. But to this day, meaning before we start to apply the cold molecule technologies to it, there is no quantum state resolved spectroscopy data that's been ever collected on C60, because it's actually very complex when you have 60 atoms interacting with each other. Just imagine you're trying to understand all the modes of how the surface distorts itself, how the soccer ball actually rotate, how they vibrate, and coming from the basic principles of quantum mechanics to trying to understand how all these different motional degrees of freedom couple to each other, rotational, vibrational, with involving 60 atoms. It turns out to be very difficult. So I'm going to tell you a little bit, actually a fairly simple way to tell you the power of cooling of molecules down, so that you can start to do this quantum state resolved spectroscopy. And so if you have a C60 like this, there's internal structure, low vibronic eigenstates you can describe. You can have these molecules interact with external excitations. You could put photons on there. You can also have this molecule collide with other species, and there's a collisional scattering dynamics. And it would be interesting to let you know now, even in 10 slides later, I will show you that we can gain a lot of information of how this molecule interact with photons, external collision partners, just by cooling them down a little bit, and gain the capability of doing this quantum state resolved spectroscopy. And so that's really the power of cold molecules right there. When we started a few years ago trying to see spectroscopy signatures of C60, we saw nothing. Well, we saw this absorption as a function of the wavelengths of the laser. This is at the 8.5 micron. The bottom axis is the wave numbers. But inverse of that is actually the wavelengths of the laser that we use. So when we were looking at the molecular absorption of the C60, what you see is this broad structure. And this is what everybody else before us had done. Is there a question? No.
No, there is no question. Sorry.
Okay, and so this is natural, because when the temperature is relatively hot, we were doing this experiment in the room temperature. All the quantum states are merged into each other, and it's just impossible to resolve them, the structure. On the other hand, as I mentioned earlier, C60 is actually a very unique system because it's big, right? You have 60 atoms. In fact, nowadays, you hear people talk about quantum computer, they talk about 60 qubits, 50 qubits. So you have 60 systems, 60 elementary quantum particles, C60 60 carbon atoms connected together, and they can give rise a unique feature of understanding how their interactions gave rise to many-body physics. 60 atoms is already kind of a unique closed quantum systems, and you can study its coherence, you can study how it's opening to interact with outside the world. So it's a kind of an interesting Goldilocks place to study finite quantum systems, and yet it's a very complex system at the same time. So we bring together some technologies such as frequency combs I mentioned earlier, very, very briefly, and the molecular cooling. So if you look at this molecule, we actually, instead of study C60 right away, we actually practiced on some less complex molecules and also less symmetrical molecules. In this particular case, adamantane is a molecule that we studied, C10H16. And as you can see, the absorption spectra at a room temperature looks very, very complex, although it's a little bit simpler than the C60, but still looks very hard to understand what's going on. But if you cool the temperature down a little bit using this technique called buffer gas cooling, there are several different groups who have done buffer gas cooling. And here I'm highlighting the contribution made by John Doyle from Harvard. And we actually learned a bunch of buffer gas cooling tricks from John's group, where the idea being putting the molecules in a cryogenic cell and have it interact with other species of molecules. Typically helium, but you can also bring in neon, you can bring in argon. They have a different, of course, temperatures that you can cool the system down to. But the basic idea is like refrigeration, right? You cool the whole macroscopic system down to a few Kelvin. In the case of a helium, it's a 4 Kelvin system, and the helium atoms coming in collide with the molecules, in this case adamantane, and you can actually cool the molecules down. As you cool the molecules down, you look at the absorption spectrum, and you can see great simplification of it, going down to 50 Kelvin, and you finally get down to 8 Kelvin. Now you can start to see, whoa, there's individual rotational vibrational lines I can actually study. It's suddenly not all the degrees of freedom, not all the partition functions being occupied. And there's a chance for you to actually understand this and this is another molecule, naphthalene, and there is a C10H8. There you can actually understand this by writing down Hamiltonians. And in fact, the red points are data, and the dashed lines here that's describing, in fact, are described by the Hamiltonian. So even with 18 atoms or 26 atoms, there's an opportunity for us to understand the system from bottom up, from a very microscopic picture of how many atoms are interacting with each other and how they are forming a rotational vibrational eigenstates. And there's not enough coupling back and forth yet so that you can identify individual absorption transitions as a signature of the rotational vibrational structure. So that's the power of cooling. And this cooling is not even very impressive. We only cooled from room temperature down to something on the order of 10 Kelvin or so. In cold atoms, we typically talk about hundreds of nanokelvin, right? So this is, but for molecules, because it's such a complex quantum system, just a little bit of cooling can open a new book, open a new door for you to study the system. And the C60 is even more dramatic from that perspective. That's just because you got 60 atoms in there. And if you write down the partition function that you learned from statistical physics as a function of temperature, and what you will see is that the partition function, this dashed line, has this exponential growth of the partition function as a function of temperature. In fact, at the room temperature, at a temperature of 1000 Kelvin, that's the temperature we typically operate our oven, where C60 molecules reside in the oven, and we heat up the oven to make the molecules coming out into our vacuum system. At 1000 Kelvin, the vibrational partition function is a whopping 10 to the 29 order of magnitude. It's just incredible. But on the other hand, because it's such an exponential growth of the partition function as a function of temperature, if you just cool it down a bit, if you cool down to say 100 Kelvin, suddenly the partition function for vibrational state can go down to 1. And so what is that telling you is that there's such a rich structure of vibration rotation going on in C60. But if you just cool down by only a factor of 3, you can reduce the vibrational equal partition function by 29 orders of magnitude. It's amazing. And actually, I didn't mention this. If you compare to, for example, a 5-atom molecule like a methane, the vibrational partition function is 10 to the 4 at 1,000 Kelvin. You can see how this exponential growth of the equal partition function as a function of the number of particles you have in your system. So CH4 is much easier to study than carbon C60. However, if you cool the temperature down, however, you can bring this into a single equal partition function of at least on the vibrational degrees of freedom. What's left, of course, there's still lots of rotational degrees of freedom. Rotational degree of freedom has not been frozen out, so there's lots of rotational states are still there. But nevertheless, you can see the basic arrangement is that we have this oven to the left side. The C60 is coming out at 1,000 Kelvin, and we bring this together to collide with very cold atoms. And sometimes we use helium, sometimes we use argon, or we use neon. We even can use molecules like hydrogen-2 molecules to collide with these C60. And we can actually study which atom, which molecule is more effective to cool them down. And once they are cooled down to, as I mentioned earlier, just something on the order of 100 Kelvin or so, then they traverse through this frequency cone. We can do spectroscopy in the middle of this vacuum chamber, and there are a pair of mirrors. Those blue things are actually a pair of mirrors where the cone light bouncing back and forth many times in this very high finesse cavity. So that allow you to enhance the interaction pathways between the photon and the molecule to give rise to a very sensitive detection spectroscopy signals for C60. So that's the basic experimental setup, very simple. And as soon as you are able to do the cooling, you can see that previously completely unresolved landscape now suddenly gave rise to this structure shown in blue. There's individual quantum states in there. And in the molecular physics, people talk about Q branch, R branch, P branch, which basically tells you the rotational quantum number is increasing by 1, or decreasing by 1, or unchanged when you're doing the vibrational transitions. And so this was very exciting for us to see when we can start to see these quantum state resolved spectroscopy signals for C60. But if you look inside, this variation of the pattern is not noise. It actually tells you some really interesting symmetries of a C60 molecule. Let me explain why. If you look at it as a soccer ball, you can have many different symmetry axes. Like here, for example, you can rotate the soccer ball by 180 degrees, and you will see the soccer ball reproduce itself. That's a twofold symmetry. You can rotate it by 120 degrees, the soccer ball repeats itself, and you can see there's a threefold symmetry. You can rotate something by 72 degrees, the soccer ball repeats itself. So you can see there's a fivefold symmetry. So there's a lot of symmetry there by the permutation of this carbon-12 nuclei. And of course, these are all bosons. So as you rotate them, the wave function has to be symmetrized as there's a bosonic system. So if you describe, well, the fivefold symmetry actually comes about because you have 12 pentagons, and you have 6 different axes for the fivefold symmetry. For threefold symmetry is because you have 20 hexagons, and that gives rise to 10 different axes. Twofold axis, you have 30 edges between hexagons, that gives rise to 15 different axes. So now these different symmetries have consequences. That means that the rotational quantum number cannot be arbitrary quantum number. In normal molecules, the rotational quantum number can be 0, 1, 2, 3, 4, 5, 7, going up by 1 unit at a time. But in C60, it's very interesting, right? The rotational quantum number can be 0. It's absolute ground state. The next one, it's not a 1, 2, 3, 4, 5, but it's a 6. That's because it's going to have a 6 different axes of 5-fold symmetry, 5-fold symmetry, sorry. And so you can't have one because there's 6 different ways of a symmetrical representation of the system. So J has to be 6. And next J is 10 because there's 10 different axes for 3-fold symmetries, and so on. So you can see the rotational quantum number is actually constrained due to the symmetry. And this gives rise to, you can actually then predict what the structure should look like. And the black lines are actually our calculated spectrum. So now let's first consider the so-called R branch on the right-hand side. If you zoom in, you can see that the patterns of the intensity exactly match what you would be calculating from the taking into account of the spin statistics of 60 bosons interacting with each other. And this is really the first time you can resolve these J numbers. They are being found on the theory front for C60 molecules. This is really the first time we can actually now confirm all these symmetries in the C60 by doing simple spectroscopy work, by cooling the molecules down a little bit. And there are, of course, open questions. For example, that on the P branch on the left-hand side, our prediction and the experimental observation do not agree. And that's actually interesting because you can actually look at the structure on certain parts. You can see actually agrees with our prediction. Other parts, on the other hand, you do not agree. In fact, you see splittings of lines. So indicating C60 molecules is more complex. This is what I would call a discovery. You start to see things that's different from your theory prediction. That's actually exciting, meaning there are energy couplings and so on. That's some interesting questions we can answer on this 60 atom system. And even more so, you can have the molecules can have many rotational lines, in the ground vibrational state. In the excited vibrational state where we're doing spectroscopy, they also have many rotational lines. As I mentioned, you can use photons to excite those. That's what we are doing spectroscopy on. But we can make photons a little more intense or less intense. You can actually study the so-called saturation behavior or optical pumping. And so because the transition dipole moment is well known, so we can actually calculate how the population is being shelved from the ground vibrational state to the first excited vibrational state or second vibrational excited state and so on. But then these molecules are colliding with the buffer gas, and the collisions will allow these individual rotational states to diffuse among different rotational degrees of freedom. It would also allow you to have vibrational relaxation because you're colliding with other molecules, atoms, and so on with lower energy. And finally, there's also elastic collisions between C60 and the buffer gas molecules. It turns out by doing spectroscopy work, by pumping it in step number 1, optical pumping, at different strength, and look at all these different relaxation mechanisms, you can actually tease out the cross sections of collisions between C60 molecules with other molecules or atoms, and find out what is rotational relaxation, what is the vibrational relaxation, what is elastic collision between those. So yeah, you can understand a lot of the C60 molecules now. And that's quite exciting time for us in terms of this very simple cold molecule system. I see there's a question coming.
Yeah, there's a question. So the question is that using the comb of such broad bandwidth, how do you couple to the cavity and how it is ensured that no molecular transition lines are missed?
Excellent question. So this must be coming from someone who actually knows frequency combs. Yes, the frequency comb, the bandwidth is pretty broad, and our mirror does not have sufficient large bandwidth to cover the entire band. However, we have mirrors. All you want is to be able to have the mirror have a spectral bandwidth that's broader than the spectral feature you want to study. So you don't have to couple the entire comb into the cavity. As long as there's a sufficient bandwidth that's coupled into the cavity that covers the spectral feature of interest of your study. That's the first question, I think. But also, and of course, you can ask a manufacturer to produce different bands of your mirrors. And we do in our lab. In fact, we have, a comb can cover 3 to 5 micron or 8 to 10 micron. You can ask the manufacturers to produce mirrors, which are, 300 nanometer bandwidth, but they can produce different pairs so that you can use different cavities to couple them if you needed to. And of course, this is as a technological frontier to continue to produce broader bandwidth of mirrors, which would be extremely powerful to have. And I can tell you one thing that we actually recently are studying, because of the pandemic, we are actually taking this comb spectroscopy. This is something not related to cold molecules, but since you asked this question, I actually think it's a very interesting application of comb, which is we are trying to study people who are COVID positive and see if their breath is different from people who are not COVID positive. And if this turns out to be possible, then we feel that this could be a much better technique to, instead of just measuring somebody's temperature, if you can just ask someone to come by a test station and they donate a breath to you, and we can use lasers to tell you, you better be careful, your breath looks a little COVID. And we don't have that signature yet, but what's really interesting, because you asked, the question prompted me for that, you want to have a very broad bandwidth to study the people's breath. Our breath have hundreds of molecules, and our sensitivity is now very good. If I have a student eat a banana, just one piece of banana, and you wait 1 hour, his breath will have increased methanol coming out, parts per trillion, parts per billion. And we can see those. So this is the hope that spectroscopy like that could actually have real practical use as well, just more than for fundamental science, of course. So I hope that answers the question, and sorry for expanding that a little bit.
So there is one small question, and that is, how can we tune the spacing of frequency combs?
Yeah,
that can be a short thing.
Yes, and that is the spacing between frequency comb is called the repetition frequency. This can be tuned by changing the cavity length, but it's not dramatically tunable because the cavity length, you can only tune certain parts, right? So what people tend to do is you can have a different frequency combs made, and you can, again, use a different repetition rate to control. But most of the time, you actually do not need to tune the repetition rate. What you want is, you have a frequency comb like my finger. What you want is to be able to tune the whole finger across. That way you can cover all the, there's gaps in there. There are some, I think the earlier question was asking, how do you make sure you do not miss any one of those? And we actually do actually tune across such that at least this finger will replace that finger. So at least I'll cover like this. And once you do that, you can see my spectroscopy signature has covered the entire range within the bandwidth that I have.
Okay, thank you. So I think there are no other questions, so maybe you can go ahead.
Perfect. Thank you. So let me move on to the next topic. I think I have 30 minutes left, right?
Yes, you have 30 minutes left.
Okay. So I'll go a little bit faster. In fact, yeah, so I think it's okay. I should be able to just about to finish the laser cooling.
Yeah, that's okay.
Let's see, the understanding reaction pathway. Maybe I'll go a little bit faster on this topic, but just I want to give you a sense of why the cold molecules can be really exciting for chemistry on chemical reaction side. For example, we all know about OH-CO reaction. This is actually happening every day in atmosphere. This is what sunshine breaks the water molecules down, and you make OH free radicals, which can interact with the CO. That's a carbon monoxide sort of a pollution, and they can react with OH molecules called free radicals, and produce hydrogen plus CO2. This is actually, in fact, a very important way of removing CO emission from our atmosphere. And of course, you have CO2, which give rise to the global warming and so on. But that's part of the fossil fuel combustion chemistry people understand. So this chemistry is sort of chemical reactions being studied for 6 decades, right? People are very interested in this. And there are a lot of theory proposals saying, these kind of a reaction does not happen in one single step. You do not produce hydrogen and CO2 right away. You actually produce the so-called intermediates. And the intermediates is called HOCO, H-O-C-O. And you can have different forms of HOCO. You can have a trans HOCO or cis HOCO, meaning this molecular bond angle is different. And again, there are a lot of theory papers written about HOCO, but there were no direct observation of this reaction pathway actually proceeds according to this prescribed theoretical model, this so-called intermediates. But there are lots of theory, and people sort of can do first principle calculations because this is still a relatively simple molecule, OH plus CO, this full body physics, right? And so people have studied it. If I have OHCO as a reactant, as they come in, they form different transition state intermediates. You can have a trans HOCO, you can have a little potential dip for the cis HOCO, and these molecules are supposed to exist, but then they will tunnel out. These are called intermediates because they don't last very long. They disappear. Eventually, what you see is a reaction product of hydrogen and CO2. But how do we really understand this potential landscape actually exist in the experiment rather than just in theory landscape? And so that what we need, again, the cold molecule can really help play a big role where you can prepare these molecules in individual well-defined quantum state. And then you develop techniques, intermediate and product states can be identified and tracked. Therefore, you can track the entire kinetics of the chemical reaction in real time. So, and I can just give you some cartoonish picture of why this is interesting. So the OH and CO come together. They can have some sort of a reaction where they're hanging out with each other, kind of doing a little dance. And they can, if you don't do anything, they are highly excited vibrational state. Eventually, they can dissociate into a product of hydrogen plus CO2. But what if, when they are in the intermediate state, some other molecules come and collide with them? And essentially, you cool them down to the vibrational rotational ground state here. Then they become stabilized. Then these molecules will actually live there for a while before they tunnel out. So then you can actually study the formation of these trans cis HOCO molecules as intermediates. So the idea is really develop certain tools where you can watch the incoming reactants, the final products, but as well as the intermediates. If we can do that, then we will be able to study the entire formation, isomerization. When I say isomerization, meaning trans and cis can actually change back and forth because after all, they can tunnel back and forth. This process, all these rates are unknown, are theoretically postulated, but with the techniques of, again, frequency comb, you can actually study this. For example, you start OH plus CO, you get them started in the middle of the pair of mirrors, you put a frequency comb in there. We actually arrange the comb to be dispersed in a two-dimensional plane so that each frequency comb component, each color, becomes a dot on a CCD camera. And you can just take camera shots, one every 5 microseconds or so. You can actually watch the chemical reactions taking place, going through trans or cis HOCOs, and then finally going to a final products. And what we do is taking just a series of shots on the camera, and each shot represents a frequency map of comb spectroscopy as a function of time. So you can actually see initially, for example, it's all reactants, and by the intermediate time scale, you see the rising of trans and cis HOCOs, and finally they go away and you have a product. And this whole process can be watched in real time. This is actually real experimental data converted from those camera images, where you can actually see the initial OH as you produce them, and they gets removed because they get participating in reactions. And you can see the rise of a trans and the cis HOCOs, and it eventually disappears. after a millisecond or so, and then the product comes up. So this whole process can actually be watched now, this chemical reaction process, using tools like that. So that's just a very quick short story about giving you one example of where the fun physics of studying cold molecules and tools of studying cold molecules can be used to apply to understanding physical chemistry. I'm not a chemist at all, completely a physicist, but I'm thinking about some problems from the physics point of view, and actually provides sometimes surprising perspective for physical chemists. They actually like it in a way that it's not just liquid or not just the soft condensed matter physics now, biochemistry, and this is a more fundamental aspect of physical chemistry, and I would call it chemical physics maybe. Finally, I'm going to tell you a little bit about laser cooling. If there are no questions, I'm going to move on to the next 20 minutes to tell you about laser cooling of molecules. Laser cooling of molecules is very hard, and partly because again, going back to the structure, you have atom where you have just electron moving around the nucleus. And we all know in order for laser cooling to work, you needed to have this many exchange of photons. So you want the atom to continue to absorb photons as you tune to the right frequency. They absorb photons from incoming light, and then they give spontaneous emission. And every time you give spontaneous emission, you have, of course, a recoil. But that recoil is random, while the photon absorption is directional. And so if you keep doing that, after hundreds of photons or hundreds of thousands of photons scattering, you finally can make atoms cool down, from moving from hundreds of meters per second to moving by about centimeter per second. That requires many photon scattering event. So a key thing in laser cooling is always the so-called cycling transition, meaning this photon can go back and forth in these two-level systems many times. And immediately you can tell the molecule is going to be a different story, right? As I mentioned earlier in the introduction, the molecules have many energy states. So the fact that you have two nuclei for diatomic molecules alone, meaning that as you drive it, that when you drive the transition from blue to the red states, as you drive the electronic transitions, the decay can come down to many vibrational, rotational states. And if you're not careful, of course, you would need to use many lasers to be able to create a cycling transition, and it seems to be out of touch. The laser requirement is too hard for us to really do that experiment. So this was considered very difficult, but turns out there are solutions. And credit this guy, Michael DeRosa, back in 2004, he suggested the first solution is so-called nearly vertical Frank-Condon factor. What does he mean by that? When you drive a molecule electronic transitions from ground to the excited state, the molecules is going to decay down from the excited state. So you're driving vibrational ground state to vibrational ground state. If the molecule decays to a vibrational ground state here, that's good, because that's part of the cycling transition you wanted. But the molecule can also decay to the vibrationally excited state, like a V double prime equals to 1 and V double prime equals to 2 and so on. So there's a whole series of vibrational states can be opened up. But you can find a certain class of molecules, actually classes of molecules, where the Frank-Condon factor, meaning the nuclear wave functions in the different electronic potentials, are nearly orthogonal for different vibrational state, meaning that if you go from V equals to 0 to V equals to 0, it has a 99.4% chance it's going to come back to the same vibrational ground state instead of going to the others. That's not always true. For general class of molecules, this is not true. The molecules will like to go to many different vibrational states, but you can select certain molecules where this is not the case. And you can see why that's important. That's because suddenly you don't have to care about other vibrational states. This is coming back to the same vibrational state. But there's another question. So even if you can close the vibrational ladder, well, there's also a rotational ladder. And this is something that we proposed in 2008, which is if you have, well, in driving the rotational enclosure to make sure it's a cycling transition, we actually use this inverted delta J equals to -1, meaning you want to go from ground state J equals to 1, not a 0, but rather J double prime, meaning in ground state rotational quantum number is 1. You drive into the excited rotational quantum number of 0. So that's why delta J equals to -1, because you're going from 1 to 0. Why we want to do that? Because once you go to 0, it has to come to 1. Or it could go to 0, but that symmetry rules will forbid that. 0 to 2 is also forbidden, because that delta J equals to 2 is also forbidden. Photon carries away only 1 unit of quantum mechanical momentum. So if that's the case, you sort of guarantee yourself that if you go from Frank quantum factor being nearly vertical, so the vibrational state comes back here, rotational state, I'm going from J equals to 1 to 0, 0 will have to go back to 1. Well, I'm close now. And this is actually true, except there's one caveat. When you have more ground states, quantum states than the excited state, we all know that when you have a more manifold in the ground state, then you're going to create a so-called dark state, meaning that the molecules, after a few optical pumping events, they will arrange themselves into a quantum state where they no longer couple to the photon field. And it's actually very easy to understand. It's just basically being driven by the Hamiltonian. Like you have a photon atom coupling, and as you keep pumping it, eventually it's going to, the atom or molecule is going to be pumped into a state which is no longer interacting with the photon. And this is so-called dark state. Once you get into the dark state, it turns itself off from interacting with the photons, which is not what you want. You want the molecule to keep scattering photons because you want to exchange that photon momentum to slow you down, right, to do the laser cooling. So we have to somehow break the dark state. We call it brighten the dark states. And what we did back in 2008, when we first made a proposal, we said, well, you can break it by switching back and forth. And in 2013, we actually demonstrated using magnetic field and the polarization. You can switch the polarization back and forth such that blue and red, there's a different polarization state of the light that's pumping it. So you can switch the polarization back and forth, such that not a single quantum state can be turned into dark. They're always, once you get into the dark, you have to change the polarization state of your light such they have to be bright again. And so by doing so, you can basically destabilize the dark states to keep the photon scattering going. And this will allow you to eventually make a magneto-optical trap.
There is a question, if we can ask.
Yes, please.
So to start with, you need to prepare the molecule in J double prime equal to 1 state. How do you do this?
Yes, you do some of the work, for example, buffer gas cooling. So indeed, you're right. If the molecules are in room temperature, there will be multiple quantum states there. And you can think of the following. If I start to cool on J equals to 1, in some sense, other molecules, J equals to 2 and 0 and 3, they are going to be gone because they won't interact with the photons. So eventually they just leave your systems. And the one that's only survive the J double prime equals to 1 quantum state. So that's one answer. And you may not be totally satisfied with that answer. You will say, okay, you're only selecting a fraction of these molecules. And that's true. But you can help yourself by, for example, doing some initial state cooling. Buffer gas cooling to 4 Kelvin is actually quite decent to focus most of your population into the lower J states. But you won't be, this kind of a cooling won't be giving you a single quantum state cooling. And in the end, your laser cooling will have to select that particular quantum state. And that's the quantum state that's going to survive through the laser cooling, because other molecules, since they do not exchange photons with, they do not get slowed down. So they're just hitting the walls. They're just gone from your system. Okay.
Okay. Yeah, I think.
So I just mentioned about rotational enclosure and then talked about the destabilized dark states, and just give you a very quick sort of rundown about how this field is progressing. It's actually witnessing very rapid progress right now. we know that 70s when the laser cooling of concept initially was proposed, 80s was the golden time of laser cooling of atoms, and 90s led to the BEC and so on, and the optical lattices in the 2000s. But the molecules actually really, like the first De Rosa proposal was in 2004, the diagonal Frank Hunting. Our proposal of selection rules for rotational enclosure was 2008. These were both theory proposals, but was very quickly followed by experimental demonstration by David DeMille's laser cooling of strontium fluoride in 1D, our own work of a 2-dimensional cooling of YO molecules, and then now 3-dimensional cooling and trapping, again by Dave, strontium fluoride, and John Doyle and Mike Talbot was able to cool the calcium fluoride down to 5-6 microkelvin. And now we have cooled the YO molecules to microkelvin and putting them into the optical lattice. So all of this is happening. In fact, I should say 2021 because it's already happening now at a 1 microkelvin temperature. I will show you in the final slide. And to just give you a very quick, it's not that I want to let you learn about YO molecules, but just this is kind of a teaching principle of why we picked YO molecule. You can see the reasoning. We picked the YO molecule is that the Frank Hunting factor is pretty good. You look at it, 0.9944. So V equals to 0 to V equals to 0. There's a 99.44% chance it's going to come back down to the same, to the same V equals to 0 state. And V equals to 1, V equals to 2, there's some percentage of opportunities going down there. We actually repump them. We actually have 2 lasers to repump from V equals to 1 to V equals to 2. Now, the second one is the rotational enclosure. And you can see I'm pumping out from J equals to 1, we call it N equals to 1 state, to N equals to 0. Upstairs, J equals to half because the electronic angular momentum is half. And finally, there's a nuclear spin hyperfine structures. And that's something I don't need to really belabor the point, except to say there are 2 hyperfine main structure, G equals to 0, G equals to 1, that we have to cover them. But we can use microwave pumping to cover that. Okay, maybe I'll just also very quickly tell you about the concept of type 1, type 2 mod. Some of you may have experience in atomic mod already, or maybe also molecular mod. But in atomic mod, for example, the typical structure you will see is a so-called type 1 mod, where the excited state have angular momentum that's 1 time, +1 from the ground state. So the structure looks like this. You can think of F equals to 0 to F equals to 1. And under Zeeman shifts with a quadrupole anti-homohost coil, you have a structures deformed like this. And if your laser detuning is done just right, you can keep pumping the atoms as they try to leave the region of your mod to scatter them back into the center and cool them and trap them simultaneously. And that's a typical so-called atomic magneto-optical trap arrangement. But remember, since we proposed to break the rotational to making sure the rotational enclosure is maintained, we want to go from J equals to 1 to J equal to 0. So you can see it's inverted. The ground state has more angular momentum manifold than the excited state. And in that case, there's a possibility to have a dark states. How do you break the dark state is what we can make the magneto-optical trapping of the molecules. So one way to break it, as I mentioned earlier, is to switch the polarization. You can switch polarization back and forth, back and forth. But remember, for mod to work, the magnetic field, the anti-homohost quadrupole field of the magnetic field has to match with the polarization of your incoming light to be able to cool the molecules down. So what we do is, as we switch the polarization, we also switch the magnetic field. The technical challenge of this work is that the switching has to be happening at a speed matches with the spontaneous decay, meaning if the lifetime is a few microseconds, you have to switch your polarization at a microsecond time scale. And we all know switching magnetic field at microsecond time scale is very difficult. So what we do is, in fact, we actually driving the magnetic field coil in a resonant tank circuit so that we actually modulating the magnetic field sinusoidally without switching. And the sinusoidal modulation gives rise to the magnetic field changing. And that's the concept we introduced that we call the radio frequency mod. And that works quite well. There have been other techniques, particularly Mike Tarbott's group proposed as so-called a dual frequency DC mod. They do not actually switch the polarization or switch the magnetic field. Rather, they use two different polarizations, both sigma plus and sigma minus, interacting with both manifolds of the inverted structure, such that they can destabilize, again, because in three-dimensional mod, you can destabilize the dark state. And this DC mod techniques has also been realized in a number of groups now. I think there are a total of 4 different groups who have demonstrated laser cooling of molecules. Harvard is Doyle, Mike is in the Imperial College in London, DeMille is at Yale and recently moved to Chicago, and then my group at Jella. So all of the groups now have demonstrated both IF mod and DC mods. And somebody was asking earlier about, well, how do you prepare the initial state? So this was my answer was, well, you can have these molecules, like in this case, YO molecules, initially gets cooled by buffer gas cooling with helium. And at the full K, they're coming out. Most of the population is the lowest couple rotational states, and we just throw away 0 state. The n equals to 1 state gets slowed down by the vibrational, by doing the directional cooling, by shooting the laser beam against the YO beam. And then once it's cooled down to 5 meters per second, we can load them into the MOP, into the magneto-optical trap. And we can typically capture 100,000 molecules. That's a fairly large number of molecules, cool them down to a few millikelvins. And then we introduced this technique called a Sisyphus or gray molasses cooling. The idea, again, is making the polarization in the space to be varied. So you have a local polarization. The molecules, on the other hand, will be polarized according to the local polarization of the light field. And again, they will have a dark state and a bright state. If the laser is detuned to the blue side of the transition, the bright state will have AC stock shift described in this pattern. And this is a shifting back and forth is because the polarization, local polarization is changing. And so if the molecule is in the bright state, it will be climbing a potential hill because AC stock shift is tuned to be rising because you are blue detuned. So the energy is AC stock shifted is rising energy. So the molecule will be climbing this hill. By the time they get to the top of the hill, this is the place where you also can experience the strongest, because that's where the light is the brightest. You will do the most optical pumping yourself through excited state into the dark state. Once you're in the dark state, you have turned yourself off. You're no longer interacting with the light. So you're moving around. But at the place where if you're moving really slowly, you can always be in the dark state. It will never come out. But if you're moving a little too fast, meaning the molecule is still a little too hot, you can have non-adiabatic transitions from the dark state back to the bright state when the energy is a gap is the smallest. You have this non-adiabatic transition, this avoid crossing. If you move too fast, you can transition to another quantum state. So you go back from the dark state to the bright state. Once in the bright state, you climb the hills again into the top, you get pumped back into the dark state. Now you can already see a very nice cooling cycle. Every time you're going from dark to the bright, you lose energy. But when you pump back to the dark, you do not lose energy because the energy is carried away by photons. And then you do a non-adiabatic transition back into the bright state, gets cooled again. So this technique turns out works really, really effectively because it's not just the photon energy is being removed, it's actually being removed by the entire AC stock shift energy. So by doing this, we were able to cool the molecules down to very, very low temperatures. And in fact, there's another trick where in YO molecule, remember I told you there's a 2 hyperfine state, and I can call it F equals to 1, F equals to 2. And they both can access to the excited state here. And you can actually drive either one of those that can do this gray molasses cooling. But you can also apply both laser fields simultaneously, almost give yourself a little Raman resonance between the 2 ground state there. And this is so-called lambda enhanced gray molasses. The structure looks like lambda. And so we use 2 different lasers, and you can actually figure out each laser's gray molasses cooling. Like for example, in this case, I put L1 to be polluted tuned, L2 to be just resonant. And so L1 is the one producing the gray molasses cooling, and I can measure the temperature at 10 microkelvin. And I can reverse the role, making L2 to be the gray molasses cooling. And again, I get a 10 microkelvin. But then I can make both of them to be on the gray molasses and also have a Raman resonance condition met. And you can actually see the temperature cools down also in the middle of the Raman resonance to a 4 microkelvin. So all of that can be played around. It's actually great for, this is after the gray molasses cooling. You can see as you drop the molecules by gravity, it's hardly expanding because now they are cooled down to a few microkelvin now. So I do want to get, I don't think that this is a really important technical detail here. The final thing is you can also play tricks by spatial compression. For example, when if you have a harmonic trap, when temperature goes down, of course, spatial density goes up. But what we do is that we can do mod, which allow you to compress. But if the mod is applied for too long, the temperature actually rises to a relatively hot, higher temperature. So we do a little mod compression, and we follow it by doing gray molasses cooling. And then we do mod compression again. So you can see that instead of realizing the mod size in equilibrium, we actually stop the mod at a very compressed low level. And at this point, we stop the mod, we turn on gray molasses to cool. And then after cool down a little bit further, because the gray molasses does not have spring constant to force the molecule into the middle, gray molasses is just cooling. So you use the mod to compress them, you cool them, and you recompress again, and you cool them again. 3 cycles later, we can actually get to a phase space density to 3 × 10⁻⁸. And most recently, we were able to actually cool the YO molecules directly in an optical lattice. And that improved the phase space density by another factor of 100. So now we are at a phase space density of 3 × 10⁻⁶. This is still a million orders of magnitude below the phase space density needed for quantum degeneracy. But for the laser cooled molecules, this is now the highest phase space density indicated by the spread point. So still fairly far away from 1. Tomorrow's story I will tell you is actually phase space density of 1. But that's a different technique. This is a technique where we use only laser cooling of existing molecules to this low temperature and this high phase space density. And I think it will be very exciting to start to see how these molecules can be evaporated and so on. So I think that's the end of today's lecture. If there are further questions, I can entertain a few of them. Otherwise, I will see you tomorrow and tell you really kind of deep into the quantum degeneracy and tell you a bunch of new exciting quantum resonances in molecular interactions.
Okay. Thank you for a very nice talk. So I think we have at least 2 questions so far. So yes. One is about this blue detuned cooling, and the question is this similar to Sisyphus cooling? Yes,
yeah, it's definitely the idea reminds you of Sisyphus cooling. That's exactly right. I think it's all intellectually, it's all connected to initial the framework of Claude Continuity and Jean Dalibard proposed in 1989, 85 to 89 period, where they proposed this AC stock shift that's regulating. You know, you have they call it polarization gradient cooling, and so you know, on the left hand side is actually a picture of the Steve Chu's group when they were initially doing the laser cooling with a ling perpendicular ling polarization to describe the polarization gradient, where the molecules, or at the time, of course, it's all atoms, how the AC stock shift is following the polarization gradient. So from that perspective, yes, it's exactly the same spirit.
Okay, so this the other question is, does one also expect sympathetic cooling due to the shelved slow-moving dark molecules?
Can you repeat the question again?
Actually, I can ask him to ask the. Saikat, can you go ahead and ask your question maybe directly?
Yeah, my question was that since you're like the slow-moving dark molecules are already cold, so is there a further additional cooling of the bright molecules because of those
Yes.
They're like a shared molecules then.
Yes, that's right. Actually, in fact, when the surface cooling was initially proposed, and there's a VSCPT and all these Raman resonance cooling, the idea is that once atoms or molecules falls into the dark state, if they're moving really slow, they will never come out. You won't have this non-adiabatic transition come into the bright state. So they will just stay there. And that's actually what you want. You want to build a little sort of a little trap hole for the molecule to fall in, and they will never come out. But what you describe is a collisional process. The molecules in the dark state, which are very cold, they can collide with the molecules in the rest of the system, which is still being cooled down. And that process, of course, is happening if you have a sufficient density. If the sample of the molecules is sufficiently dense, there's a collisional process going on, then that, of course, gives rise to the thermalization between the molecules. But that's not always guaranteed. You need it. In some sense, sometimes it's a chicken and egg question. If your molecule density is really low, you actually do not have these collisional process happening at a sufficiently fast time scale to ensure thermalization. So the light cooling is the only way you have. But as you cool down further and further, the spatial density will increase. At a certain point, they will kickstart the collisional process. And so, yeah, so that I wouldn't call that as a really necessary sympathetic cooling, because it's in the end, it's the same species that's happening. Some of them experience the more laser cooling, but in the end, their roles are changing all the time. There are techniques now, people are trying to bring atoms, in some sense. Wolfgang Ketterle's group in MIT, in my group, tomorrow actually we'll talk a little bit about that. You can bring cold atoms together with molecules and use cold atoms to cool the molecules down a bit.
Okay. So I don't see any other questions, so maybe I can ask this question. So this is related to so we know in this ultra cold, even KRB, when the two molecules come together and collide, there is some losses. So when going further in this strontium fluoride or ytterbium monoxide, but ultimately you would like to do some kind of evaporative cooling or something. So yeah, do you see roadblocks there? Or?
Yeah, no, excellent question. This is a sort of the question that's been outstanding in the cold molecule field for the past 2 decades. The very question you ask is, in order for evaporation to work well, you want elastic collision to dominate over inelastic loss, and that's why it's taken a long time to overcome all these problems. And tomorrow, actually, I will specifically address your question about how do you tune up the elastic interactions without increased inelastic loss. So the KRB, and we towards the end of last year, we published 2 papers. A pair of them came out all at the same time, one in Science, one in Nature, that really showed that you can use electric field to shield the loss, but it still allow you to have elastic collision to move forward, but the loss is being shielded. So being able to control this elastic over inelastic ratio, you can really get yourself into this favorable regime of evaporation. And that's a key. And so for laser cooled molecules, there is no such study yet. I think none of our molecules at the moment are having been studied on these, how do you tune the interactions of elastic versus inelastic. There's some work going on in John Doyle's group where you can use I field to shield the loss, but they haven't demonstrated, elastic collisions exist in those systems yet. But in the KIB, I will show you some results tomorrow that by shielding the loss, we can actually foster the elastic interaction to play a more dominant role.
Okay, thank you very much.
So it's getting late in India, right? It's you're 9:30 p.m. Is that correct?
9:40. Yes, that's right.
Yeah, you guys should go to sleep.
No, we go to sleep a bit later, so it's okay for us.
Okay.
So we wanted this to be this session, evening one, to be such that people from the US can actually join in at a reasonable time. So actually, all the speakers from US are at this slot in the evening, so it's okay. for us.
Yeah, I appreciate that.
No, that's fine. That's fine. Okay. Thank you, Professor, for a very fantastic talk. So, and I will see you tomorrow again at the same
We'll see you tomorrow. Yeah, have a good night. Bye-bye.